second. So to compare this multiphoton pi pulse scheme with single pi pulse scheme, the idea was to plot the time evolution of the population transfer using a single pi pulse where these intermediate levels were completely absent. In this case, to transfer from the 5s straight to the 11p3 half. So what we can observe here is that the case of the population transfer using a single pi pulse photon is suppressed as a result of the AC stack shifts which are imposed by the dipole allowed transitions leading up to the excitation of this 11p3 half between the ground state and the excited state, which we calculated the AC stack shift for the case of going beyond the rotating wave approximation, producing a detuning of about 160 per centimeters, which is very close to the line width of the 75 femtosecond pulse. So in order to understand the effects of this detuning caused by certain effects, and also in order to understand how detuning influences the study, we consider the effects of detuning by tuning the laser frequency to be slightly off resonance for the red detuned and blue detuned pulses. So considering different ranges of detuning from -400 to 400, what we can see here is that in the case where the line width is very close, in the case where the detuning is very close to the line width, we observe a suppression of down to about 10% of the populations being transferred. This shows how these AC stack shift effects could influence the population inversion, and also detuning is also detrimental to the population inversion. So the final part of this study was to compare the cases of going beyond the rotating wave approximation as we did, and also the case of the rotating wave, working under the rotating wave approximation. The idea of going beyond the rotating wave approximation to account for all Fourier components of the pulse interacting with all dipole transitions of the system, we're able to see the effects of other on the other transitions, which we can see here in the case of the second transition and the case of the third. But on the other hand, when we work under the rotating wave approximation, the fields are coupled only to their respective transitions. As a result, these effects seen here are not seen in the case of the rotating wave approximation, which we can see here in the figure A. So the goal of this method was to demonstrate ultrafast coherent excitation of Rydberg states by demonstrating its applicability of the method of the pi pulse scheme, and also showing how these multiphoton processes are required as a result of the inapplicability of using single pi pulse scheme, and also the possibilities of its extension to numerous geometries and other systems. So the next part of the thesis talks about the multi-dimensional time resolved spectroscopy. So what we studied here was quantum control spectroscopy of population transfer and vibrational states using chirped pulses in the 4-level density matrix equations. And here we considered oxazine systems as the typical case study. So the idea here was to study enhancements as a result, enhancements of these population transfers and vibrational states. So in multi-dimensional time resolved spectroscopy, a very important method for experimentalists which can be related to our density matrix model is the transient absorption spectroscopy. So the idea of the transient absorption spectroscopy using the pump-probe method is that it involves two pulses, the pump pulse serving as the excitation pulse used to excite the sample molecule, and the probe pulse being a delayed pulse used to interrogate the changes caused by this excitation pulse with the signals collected by a detector and with numerous contributions to this signal. So how does this transient absorption spectroscopy relate to our density matrix model? Simply that the information about the time evolution of the populations can be obtained from the signal level of the transient absorption signal, while the oscillatory amplitude of the transmission of the transient absorption signal relates to the coherences. So here we wanted to study oxazine systems, using oxazine systems as the case study by summarizing its active mode to a 4-level system having 2 electronic states, which these electronic states have 2 vibrational levels, with a separation between these vibrational levels having a vibrational frequency of about 600 per centimeter. So the idea here was to use oxazine systems by considering parameters that are typical for oxazine systems, where we consider weak intensity fields, and as a result, we worked under the rotating wave approximation, where we consider the relaxation times for these populations and for the coherences, and also considering the vibrational coherences which are represented by rho 1, 2, and rho 3, 4. So the idea here was to consider parameters that could influence these enhancement studies by considering population durations, which was varied, and also spectral chirp and the dephasing rates. So the idea here was to study enhancements of populations in the ground state and in the excited state. So the enhancements being the ratio of the values calculated for the chirp pulse and for the transform limited pulse. We were able to plot the enhancements of the vibrational coherencies and for the populations transfers for the ground state and for the excited state. And what we can see here is that we plotted these enhancements as a function of the spectral chirp and also as a function of the frequency wave number. So what we see here is that these blue regions correspond to suppressions, while the red regions correspond to enhancements, with an enhancement of about 2% to 20% for the first three cases. And then in the case of the fourth figure rather, we observe two characteristic peak points, which corresponds to enhancements of about 4.3 and 3.5. So the idea was to understand what are the processes that are occurring behind these enhancements. So we took a cross-section of these enhancement plots and then plotted for particular frequency wave numbers for enhancement in the ground states and enhancement in the excited states population. So the idea was to plot the time evolution of these particular points taken for specific chirp values and also for specific frequency wave numbers, which were plotted for the ground states and for the excited states. And we can see that these enhancements, the enhancements seen in the first case, here, here, and here, corresponds to optimized pumped up intrapulse processes that occurs to and fro these ground and excited states. Also, we also consider the influence of pulse duration. So, the idea here was to see the dependence on the pulse duration by considering two pulse durations, 30 femtoseconds and also 17 femtoseconds, by considering time broadening of these transform limited pulses, achieving a bandwidth comparing to the vibrational frequency. So the idea, what we see here is that there's similar qualitative behaviors comparing the 30 femtoseconds and the 17 femtoseconds. But in the case where the chirp is being varied, we see more undulations in the case of 17 femtoseconds as a result of the longer broadening of these 17 femtosecond pulses as a result of the larger effects of chirp. So the final part of this study was to consider the effects of the dephasing time. So the idea here was dephasing time being an inverse of the dephasing rates. So considering these dephasing times being ranged between 5 femtoseconds and 200 femtoseconds, we wanted to study how this dephasing time influences the enhancement of the population transfer and the vibrational coherencies in the ground state and in the excited state. What we can see here is, in the cases where we use 5 femtosecond dephasing times, we observe a complete destruction of the enhancements. But in the case where we increase these dephasing times, we observe these enhancements and also the suppressions, similar for the case of the ground states and the excited states. In the case of the vibrational coherencies, we observe that the enhancements are seen only when the dephasing times are much longer. But when we consider 5 femtoseconds, we observe this destruction in the enhancements dropping down to 0. So the goal of understanding enhancement is to be able to improve selectivity in controlling these physical processes in chemical reactions, and also to control the selectivity in transferring from an initial state to a target state in order to achieve higher precisions and also to suppress unwanted quantum channels. So the final part of the thesis deals with the study of ultrafast processes on the attosecond time scale. So what we did here was we used the density matrix approach. We use the density matrix approach to model laser dressing dynamics on core transitions in krypton atoms, where we considered the laser dressing dynamics and compared our simple theoretical study to a more detailed experimental study done by the group of Professor Joseph Serres. So, understanding transient absorption spectroscopy, let's take a look at the attosecond transient absorption spectroscopy. So, the idea of the attosecond transient absorption spectroscopy, similar to the femtosecond transient absorption spectroscopy, is that using the pump probe method, it involves two pulses, the pump pulse and the probe pulse. Here, the pump pulse is a strong near-infrared pulse, which is used to cause dynamic changes to the transitions of the target atom. And then the probe pulse is a weak XUV attosecond pulse, which is used to interrogate the changes caused by these pump pulse. So the idea is that there is a delay between these pump pulse and the probe pulse, and this delay is being varied. The variation of this delay leads to a delay-dependent absorption spectrum, which together with the atomic polarization is used to give information about the induced changes caused by this excitation or pump pulse rather. So these XUV pulses, which is used as the probe, can be generated by means of high harmonic generation as single pulses or as train of pulses using this high harmonic generation means, for example, the three-step model proposed by Corcoran. So in order to understand the theory behind this attosecond transient absorption spectroscopy, the next step will be to consider the transmission signal, which here is considered as the ratio of the pulse, the intensities, after interaction with the intensities, the incident intensities, which we can relate this transmission signal to the absorption signal using the Beer-Lambert's law, considering the atomic density and interaction length. But first, calculating this by calculating the polarization, which is taken as a trace of the product of the transitional dipole matrix and the density matrix elements. So, in order to understand the motivation behind the study, I'm going to just briefly introduce the method of the experimental approach by the group of Professor Joseph Serres. So here, they demonstrated the laser beam being focused using a concentric mirror on the gas jet in order to serve as the high harmonic generation source. So here, by obtaining the XUV spectrum for a range of photon energies covering the core transitions which are studied for the case of krypton atoms. So what's seen here is that they consider this XUV spectrum for a range from 60 electron volts to 230 electron volts with the aim of studying laser dressing dynamics and also sub-level beatings. So observing beatings in a case where two transitions are possible at the same time with close photon energies. Calculating the beat frequencies with this formula here, they observed that the beatings were seen at two sub-levels, the 3D sub-level and the 3P sub-level, at beat frequencies of 0.3 petahertz and 2 petahertz. So the idea here was they used Fourier filters and applied it to the measured data and using a window function to select these beating frequencies in order to observe the beatings. So what they see here is that in the case of the transition centered around 90 electron volts, they observe beatings more visible between -10 and 10 femtosecond.